we are discussing about detection of features, feature points, and also how do you describe those feature points uniquely, so that both detection and description becomes transformation invariant. In the last lecture, we discussed how a feature point can be very distinctive, robust to the transformation of scale and rotation, translation, and they are characterized by their position, scale, and also orientation. Now, we will be considering a description, and which is a very popular descriptor which is used widely in the image processing techniques, and this descriptor is called scale invariant feature transform. It was proposed by David Loewy in 1999. In fact, these slides are adapted from his presentation, and we will be considering how these descriptors are derived. So, we can consider once we detected a key point. So, around that key point we can take a 16 cross 16 square window. You should note that it is orientation corrected. That means, once you have the orientation, dominant orientations around a key point, then you perform the rotation to align it with your reference axis, for example, x axis, and or rather the x axis to be rotated along this direction. And then in that rotated image, now you take a 16 cross 16 square window, and let us see how these descriptors are local statistics is accumulated. In fact, there are some diagrams, I will be explaining them. So, what we need to do? We need to compute edge orientation, that means angle of the gradient minus 90 degree. So, that is how the edge orientation is defined. So, the gradient operations we have already in the very first lecture itself I discussed that you have to take the you have to compute the derivatives along x direction and derivatives along y direction. So, these two vectors they would give a direction, and that angle is the angle of the gradient. And then if I subtract 90 degree from it, you will get the edge orientation for each pixel. And then you can throw out weak edges, that means the magnitude, give a threshold over the magnitude, and then create histogram of surviving edge orientations, which are shown here figuratively in those diagrams. You can see here that here in this typically in this picture it is showing that in that 16 cross 16 window at every pixels how it is shown, of course, in a smaller window, how the directions are shown at every pixels. That means, at every pixel you computed gradients, and these are the directions. Some of them are thrown out from the consideration of the magnitudes if they are weak, and then you bin those directions into a histogram, which I discussed earlier, that because directions can be considered, it ranges from 0 to 2 pi radian angle, and then you discretize those intervals. Each interval is called binning. So, in this case, as you can see from the diagram itself, there are I think 8 directions. So, there will be 8 such intervals, each by 45 degree, pi by 4, and within that you are binning those directions, and then you can get the histograms. So, the length of the vector in this particular diagram is showing the magnitude, showing the number of pixels, or even you can add those magnitudes of gradient to get the magnitude of this histogram, to get that angle histogram. So, next what we do that you can divide this 16 cross 16 window into a 4 cross 4 grid of cells. So, in this case it has been shown 2 cross 2 in this particular diagram for typical examples, and for each grid of cells you get the histogram. So, compute an orientation histogram. So, the what I discussed the histogram of computation of the orientation histogram, that was not over 16 cross 16 cell, it was each of 4 cross 4 grid of cells, and each one will have 8 bins of histogram. So, each one will give you 8 dimensional vectors corresponding to each histogram. So, since there are 16 cells, so finally, if you concatenate all those vectors into some order, that would give you 128 dimensional descriptor. That is what is your shift descriptor. So, the properties of shift descriptor is that it is capable of handling changes in viewpoint, and there is a significant changes in illumination. Just to qualify that, it is observed that it can handle up to about 60° out of plane rotation, and it is found to be invariant even the illumination variations due to day and night. So, this is about this shift descriptor, but now there are various other descriptors. I will briefly summarize them in this particular lecture. One of them followed by shift descriptor is a speeded up robust features or SARP descriptor, which has been proposed in 2006, and this descriptor also is very popular because there are various modifications which have been introduced in this particular in computing this descriptor, so that it could be computed efficiently. That means your computational speed increases significantly using this descriptor. Mostly in the shift descriptor, the major computation that we need to carry out by using the Gaussian convolution. So, in this case, in the SARP descriptor, instead of Gaussian convolutions, what we can do, we can perform box type convolutions. That means, we can compute the same gradients or also same double derivatives. So, we will show what are the detectors what has been used in this particular case, and they can be convolved using a box type of filters. I will explain what is meant by this box type of filters. And in fact, which means in this case the convolutional masks, they have only weights of say 1 and -1, and there are patches where all are 1 and all are -1, and those patches are square patch, and that is how this kind of the shape of this filter is called box type of filters. And these computations can be carried out using an integral image, which again I will explain in this particular discussion. So, the key point detection using this descriptor, for this descriptor, that key point detection is performed using Hessian operator. Instead of the difference of Gaussian operator, we consider the Hessian operator in the image itself. So, Hessian operators are those double derivative operations in the directions. So, in this case, if for an intensity images, you perform double derivatives along x direction, then along x and y, y and x, and y directions. So, this is what is your Hessian operator, and you perform the local maxima of the determinant of this Hessian. So, once again you can perform these operations over multi-resolution representation, where the instead of convolving using the Gaussian mask, this Hessian operator itself, that means this computation of this double derivative, they are computed with a different sizes of masks. So, with increasing mask size, you are obtaining the larger scales, you are equivalently performing larger smoothing of the more smoothing of the images, which means of lower resolution representation of the images, and from there you try to capture the local maxima in that representation, in that kind of representation of images, compute the local maxima. So, we have to accumulate the orientation corrected Haar wavelet responses in this case also. So, in the shift we have accumulated orientation corrected the gradient directions, and in this case the gradient computation also is carried out using Haar wavelets, which can be easily implemented by box filters. So, I will elaborate in subsequent slides. So, this is what is the Hessian operator, that is what we have discussed here that so the convolution with Gaussian second order derivative with images, but this is actually replaced by a box filter in the SARP cases. So, key point is maximum determinant of this over space and scale. So, this is approximation. You can see in this picture how the box filters they look like. So, here you can find out that this representation. So, these values, the brighter values, they are shown by the values of 1, and the darker values they are shown by values of -1. And this is a representation which has been used here. So, it is not only 1, there could be other integral values also. So, so this is dyy. So, 1 minus 2 1. So, this is the representation, and say for dxy these are the computations. So, this is a explanation there, and the approximation of determinant of Hessian operator, which is supposed to be ideally double derivative of Gaussian masks, but we are approximating it using these box filters, and this is the computations dxx dy minus w dxy whole square, and here the value of w is taken as 0.9, and particularly 9 × 9 box filters are approximation of Gaussian width 1.2. So, I should say tricks which is used approximating convolutions using Gaussian masks or double derivatives of Gaussian masks. About the use of integral images, that is also explained nicely here in this slide. Here you can what is an integral image? Let us first define. You can see that integral image is the cumulative sum of pixel values over a rectangular region which starts from the I should say 0 pixel location. So, it is something like that over this image at every point, suppose I would like to compute the integral value at this point. What I have to do? I have to compute the sum of pixel values in this particular region, and that value will be replaced here. Now, these computations can be efficiently performed in one scan, because this could be accumulated, this sum could be accumulated over computations of other values which has been already computed. So, in one scan we can compute an integral image. Now, given that integral image, I can compute sum over any rectangular zone by using these operations. That means, this is the integral image value at these points, and if I perform, if I can see that to get the sum of this value, what I need to do? I need to take the sum over all this region and then perform the subtract these values, say over this particular and this particular term, and then the value this one, because this is twice subtracted. So, if I do that, then actually I will get the corresponding sum over this particular value. So, when you are applying box filter over a space, so what you are doing, you are simply performing either addition, or you are performing actually addition, accumulating those value, addition of the pixel values along in that region, and then in subsequently you are using this value for subtraction weighted, you can multiply it by that weight, then you are using this value for subtraction or addition. You can see the box filter implementations earlier for computing the determinant of that Hessian matrix, what we discussed. And so, every kind of computations of the sum of these pixel values, it requires only 3 additions and 4 memory access, and that is how efficiently or it increases the speed of computations. And next what I said that that is a computation of Hessian and finding out the corresponding key points by computing the local maxima of Hessians using box filters. Now, for describing the key point, once again like shift, here also around its neighborhood you are accumulating, you are collecting the statistics of the orientations, but in this case the orientations are once again computed using Haar wavelets. Once again this is nothing but in this case, as you can see, it is computation of gradients along different scales. So these are the two particular filters which has been shown here, and they can be implemented by box filters. And to get the orientation, what you can do, you can rotate the image and then apply these filters and find out where you get the maximal responses. So, the longest vector that would provide the dominant directions, and this could be implemented by box filters as we have discussed earlier also, that white portions would be, say for example, we are summing them, all those pixels in the white regions, and after summing all the dark pixels you are performing subtraction, which means in these computations, for example, if I am applying this particular convolutions operations. So, for summing up the pixels around this, we will take 3 operations for integral image. Similarly, summing up will take 3 operations. So, total 6 operations, and then you require also a subtraction. So, another additional operations, but with 6 operations you can compute to particularly these 2 values, and then you can perform the corresponding. So, 6 operations in this for computing each filter response using integral image. Actually, you require one more operation, because after that you need to perform the subtraction. So, you sum this value, you take the summations of this value. Suppose this is over region A. So, and then this is the region B, and then you have to perform a subtraction. So, this is how you can compute this particular operations. So, instead of 6, 6 is for this 3 plus 3, but this will require another additional operation. And to get the final descriptor, what we do not collect like the binning of histograms what we did in this case of shift. Instead of that, in this case, after performing these orientation corrections, we partition these square subregions into 4 cross 4, partition those regions into 4 cross 4 squared subregions, and in each region we are computing these particular quantities. That means, after performing the Haar wavelets, so we are taking the summation of the convolved responses and also the summation of the magnitudes of the convolved responses of Haar wavelets along the x direction. Similarly, those two along y directions. So, as you can see that each region, each cell of 4 cross 4 cell will give me a 4 vector, 4 dimensional vector, and there would be and size of the window is 20 cross scale, that is the size of the window, and since there are 4 cross 4 square regions, so each region will give me a 4 dimensional vector. So, you will get, so it is regularly spaced 5 cross 5 sample patches in each sub region, and then each sub region has 4 dimensional vector, and if you concatenate them, then it would be a 64 dimensional vector, and that is how the SURF response is given. So, you can see the reference of this paper is given here. For the details, you should look at this paper, which you can read in details, and you can get all this description. So, we discussed about 2 such descriptors like shift and SURF, but still they are computationally quite intensive. So, there are different other descriptors, those are proposed later, and they are also quite becoming popular in various applications, particularly where you require fast computations like in real time applications. So, one of the detector which is called FAST detector. By the name FAST, it is implying that it's a very, it computes fast the detection of feature point. So, but the acronym is Features from Accelerated Segment Test. I will have a brief description of that particular method. And also there are different descriptors like brief or binary robust independent elementary features, or WRB, which makes the description rotational invariant by considering oriented fast detection. So, fast is not a rotation invariant detection. So, but in WRB, that limitation has been overcome by performing some operations. I will be also discussing that, and also the rotated brief. So, brief is also not orientation in independent descriptor. So, in ORB, those are taken care of. So, this is the principle of detection of a key point or feature point in FAST, and there is a test which is called 12-point test, and where it considers very defined locations around a pixel, and those are shown in the diagram. The locations which are shown by the square thick square edges. So, you can say that the size of the mask in this case is about I think 7 cross 7 mask, and there are location centering this particular pixel. So, this is the central pixel, and this location. So, this is 1, 2, 3. So, if I consider these are the locations, say 1, 2, 3 like this. So, there are in fact 16 such locations which are shown here, but out of them, if there exist 12 consecutive points which are brighter than the central pixel, then we consider that point is an interesting point, which is a key point. That is the principle. So, it has been shown that this works well for detecting various key points. So, there are also modification of the strategies which improves this performance. Now, we can train decision tree on the Boolean conditions given level data. So, the details you can find in this particular paper which has been shown here. It is a paper published in IEEE Transactions of Pattern Analysis and Machine Intelligence in 2010, and it is written by Rosten et al. So, you can look at this paper and get the details. So, just a little more elaborations about this particular point. So, there are even for the decision trees, that partitioning of points on the circle, and you can train them in that as a decision tree. So, you can characterize them as a point which is in the category of darker, and a point which are similar with respect to, that is with respect to central pixel. Either it is darker than the central pixel, or almost similar, or it is brighter. So, it is a trinary logic. So, that means there are 3 states for every locations, every points which are shown out of those 16 points, and then based on them you can train a decision tree based on those values, and given the training samples of interesting key points and their neighborhoods, and use that decision tree later on to identify key points. So, the problem is the classification of points in 3 classes and create 3 partitions for a point, and then you can train a decision tree. So, now let me describe a descriptor, discuss about a descriptor around a key point. So, the previous one is a replacement of the detector operator like Harris operator, or difference of Gaussian operations, local maxima of difference of Gaussian, local maxima of Laplacian measure for SURF. So, FAST replaces them, and as you can see, the computation is very simple based on those heuristics and those principles. Now, let us see that how a descriptor also could be computed without much complex computation. So, in this case, this is the principle that we consider randomly a set of ND pairs of locations, which is denoted here a set xi yi, that is a ith point in that set in a patch centered around a point. Actually, xi is not x coordinate, xi is the point, yi is the point, and they are coupled together. So, we can perform the following Boolean test, that if px is less than py, then it would be 1, otherwise 0. So, let me explain what does it mean. So, suppose you have a pixel here, some central pixel C, and around its neighborhood you have randomly defined certain pairing of points. So, this is the point xi and this is the point yi. Then you are computing this value tau c xi yi. So, these are the positions, and then you are getting a binary value 1, right. So, you get a binary string. So, there are ND such pairs. So, you get a binary string of length ND. In fact, that is what is supposed to be a feature descriptor. So, it is an ND dimensional binary string, and as you can see, this computation is very fast, and it has been found that this is also giving a feature descriptor around key point, which is quite unique. And you can consider a value of this point also. You can since it is a binary representation. So, you can also convert this into a decimal value. So, typical dimensions which are used in experiments like 128, 256, 512, you can see that a very large dimension. But the problem is that as you can see that there is no concept of making it rotational invariant, there is no concept of making it scale invariant. Even the first also there is no concept of rotational invariant or scale invariant. So, in WordB, that is another descriptor, these are taken care of. So, here the first detector is applied on pyramid of smoothened images. So, again the multi-resolution images representation is used, and orientation compensation has been done in a very simple and tricky way, that you consider an intensity centroid. So, that is the characteristic. So, what is an intensity centroid? Say you have a key point which is given by C. Now, this is a geometric center. Now, if I consider the centroid of the intensity values, that means a pixel which contains the average of the intensity values, which is close to the average of the intensity values, then that is intensity weighted center of patch, it is not average. So, we are considering the location where intensity is acting like a weight and taking the intensity weighted central location. So, that is a different point, and this gives me an orientation. It is something like it will try to simulate the gradient direction. So, this is the orientation. So, now you describe all those, you perform all those operations by performing rotations by aligning your reference axis to this orientation, and then you can make it this rotational invariant in this way. So, rotate the patch by the angle and compute brief, and this is called actually steered brief. So, let me stop here at this point where we have discussed various descriptors, I mean other than surf and shift, which are quite computationally intensive, but there are also additional descriptors like brief, WordB, and also a fast detector, which acronym is also fast, and they are computationally efficient. So, next we will continue this discussion once again, just to understand that how these descriptors could be used in matching pairs of key points, and also there are other kinds of descriptors which are also useful in various other processing of images and analysis of images, that we will also discuss. So, let us stop at this point for this particular lecture. Thank you very much.